So today we're going to discuss the fourth section of our unit on thermodynamics, talking about enthalpies of formation. So last time we talked a little bit about calorimetry. Well, sometimes calorimetry isn't effective. The reaction takes too long and we spend a lot of time just collecting data. So the reaction's too slow. So instead we can use heats of combustion. So we can calculate our change in enthalpy from heats of combustion. And we can also use standard enthalpies of formation, which is what we're going to use today. Well, the symbol for standard enthalpy of formation is delta H, and then this little degree symbol sub F for enthalpy of formation. So this is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard state. So enthalpy of formation, we're calculating how much energy is either taken in or given off when we form some compound, whatever that is. The degree symbol indicates that it's under standard conditions, so this makes it a thermodynamic function. And then we say standard state is the precisely defined reference state. In this system, we only measure the changes, not the absolutes, meaning we don't know how much energy at the beginning and at the end. We only know like the increase or the decrease in energy, but that's all we really need is the change. And this also helps us compare substances, because we can look at the different changes. And remember, the enthalpy of formation is always given per mole of product with the product in standard state. So it's always going to be kilojoules per mole. Okay, so let's look at some different standard states. We can have a compound. That's a standard state. If we have a gas, we're going to say it's at 1 atmosphere. Our pure substance in a condensed state would either be a pure liquid or pure solid. If it's in solution, it's 1 molarity. We could also have an element. And this would be the form at which the element exists under 1 atmosphere and 25 Celsius. So for oxygen, it'd be O2. For sodium, it'd be Na. So whatever the standard state of that element is. Okay, so let's talk about how to use enthalpy, or to calculate enthalpy using standard enthalpies. You can find your standard state enthalpies in any textbook. Usually they're in the appendix or in the back somewhere, and there'll be a big chart. Okay, and we can calculate enthalpies of many reactions using these standard enthalpies. And we basically choose any convenient path, whatever reaction works, because remember, enthalpy is a state function, so we're only concerned with beginning and end, not really how we get there. And so remember we said that the standard enthalpy is the formation of the compound from the parts. So we take reactants apart to their respective elements and form the products from those elements. So, for example, we have methane plus oxygen produces CO2 and water. Let's look at the methane. Now, to get the standard enthalpy of formation for methane, we have to break it down into its reactants, or what forms it. So we know we're going to take carbon and some hydrogen gas, and if we do that reaction, then we get a standard enthalpy of 75 kilojoules per mole. Everything here is in its standard state, elemental forms, things like that. Well, this reaction, we're breaking down the methane. We want to form methane. So because we're going to switch the order of the reaction, we need to switch the sign on the standard enthalpy, making it negative 75 kilojoules per mole. Now let's look at oxygen. Well, oxygen is already in its elemental state, and so for an element in its elemental state, the heat of formation is 0. Okay, now we're going to use elements to form products. Now let's go to the product side. Well, in order to do CO2, we need to take carbon plus oxygen. Heat of formation of carbon dioxide is negative 394 kilojoules per mole, and that is going in the correct direction, so we're not going to change anything. Now, if we look at water, if you look at the balanced equation, we have 2 water molecules, and so we need to make sure that we are producing 2 water molecules here to get the correct standard enthalpy. And so we have 2 hydrogens plus oxygen goes to 2 waters. Everything is in its standard state. And if we had 1 of everything, or 1 mole of water being produced, we'd have an enthalpy change of negative 286. But since we have 2 water molecules, we're multiplying it by 2. And so to get the delta H of our reaction, we add up all the delta H's of all our reactants and products. So A plus B plus C plus D, which it represents methane, oxygen, carbon dioxide, and water. And so we have a, let's see here. Okay, so we made our methane negative. Remember, we had to switch the sign. And So we have a negative heat of formation for methane, a negative heat of formation for O2, positive for CO2 and water, because those are our products. And if you notice, we're also multiplying the water by 2. So here we have a negative times negative 75 plus 0 plus negative 394 plus negative 572, giving us negative 891 kilojoules. So we're going to subtract the enthalpies of formation of the reactants from the enthalpies of formation of products. And here's the general overall equation that we're going to use. The delta H of the reaction is equal to sum of the moles of that product times the heat of formation of that product. Add all the products together, minus the number of moles of each reactant times the heat of formation of the reactant, and then add all the reactants together and subtract those two terms. So let's take a look at an example. Okay, calculate the standard enthalpy change for the overall reaction that occurs when ammonia is burned in air to form nitrogen dioxide and water. This is the first step in the manufacture of nitric acid. So I've already written the reaction for you. Now, given that you know all the reactants and products, you could write this on your own as well. First thing that we need to do is balance it before we can move on. And so let's see here. I'm going to put a 2 here because I have 3 hydrogens and I have 2 hydrogens. I know there's no way to reconcile those. So now by putting a 2 here, I've got 2 nitrogens. So we'll see if that works. And this 2 also means times the 3 hydrogens, I've got 6. So I know I'm on a 3 out front. Well, now if I add together, I've got 3 oxygens plus 2 times 2 is 4. So 3 plus 4, that's 7 oxygens. Well, here I have a 2. There's no way to multiply 2 by anything to get 7 except for 7 halves. Now, this is kind of a trick you can use because if you make this into a fraction, then it's easy to get rid of the fraction and get your balanced equation. Because right now it is balanced, except we can't have a fraction as one of my coefficients. So in order to get rid of that, I'm going to multiply it by 2, which makes that 7. If I multiply this by 2, I get 4. If I multiply this one by 2, I get 4. And if I multiply 3 by 2, I get 6. So now my balanced equation is 4, 7, 4, 6. So sometimes if you're stuck, make something a fraction. That can make things a bit easier. Okay, well I know that it's delta H of the products. Where's my pen? I lost it. There it is. Minus the sum of the delta H of the reactants. So again, you need to look up the heat of formation in a table. I've already done that. And so my delta H of my reaction is going to be equal to products minus reactants. So I'm going to start with the NO2. I want to multiply the number of moles by the heat of formation of 1 mole of NO2, which is 34. Now all the units are kilojoules per mole. And since 4 is moles, my moles will cancel, giving me kilojoules. I'm going to add my other product, which is the water as a liquid. Standard states and physical states are very important, so there is also heat of formation for water as a gas. So when you're looking these up, make sure you have the right one. Heat of formation for water as a liquid is negative 286 kilojoules per mole. Okay, now I'm going to subtract that quantity from my reactants. So 4 times NH3, which is negative 46. And 7 times O2, well, since O2 is an element in its standard state, it's 0. And so if I add up all of my products, I get negative 1,580 kilojoules minus, and then my reactants are negative 184. So remember, negative times a negative is a positive. So if I put those together, I get negative 1,396 kilojoules. And that's the heat of reaction. Okay, let's look at another example. So compare the standard enthalpy of combustion per gram of methanol with that per gram of gasoline. So combustion reaction, I need to write my reaction. Let's start with methanol first. CH3OH. I know any combustion reaction contains oxygen as a gas. Remember, states are going to be important here. And I know it goes to carbon dioxide and water. In general, any combustion reaction has those two products. Now I need to balance. So let's see here. I see 4 hydrogens, so I'm going to put a 2 here. That makes 2 oxygens plus another 2, so that's 4. But I've got 2 and then 1, making that 3. So I think I'm going to make this whole thing a 2. So that changes my hydrogens. I've got 4 times 2, which makes this 8 now. So I want this to be a 4. So now let's see. I've got 4 oxygens plus another 2. That makes that 6. I've got 2 from my methanol and 2 here, so if I want 6 total, I need a 2 in front of that oxygen. Oh, whoops, I forgot the carbon. I'm all over the place today. So that's going to have to change. So let's see. We've got 4 oxygens plus another 4, making that 8. So I want this to be a 3, which will make it 6, plus the 2, which makes it 8. So now we should be all set. Okay, now it's the same process. So delta H of the reaction is equal to products minus reactants. So 2 times our heat of formation for carbon dioxide, plus 4 times the heat of formation for liquid water. And then all of that minus my reactants, which is 2 times my liquid methanol, which is negative 239, and then 3 oxygen in its standard state as an element, so it becomes 0. So for that first big term, I've got negative 1932 kilojoules, and my second term is negative 478. Negative times negative gives me a positive, and so I'm going to end up with 1454 kilojoules. So that's for methanol. Negative, it's exothermic, makes sense. You're burning gas or burning methanol, it's giving off heat. Let's look at the gasoline. Gasoline is C8H18. I know it's going to be the same. Liquid. Products, carbon dioxide and water, liquid. Okay, now I need to balance. Oh, let's see here. 8 carbons, but I've got this oxygen by itself, so I know I don't want that, but so I think I'm going to start with a 2 here. So by putting a 2 there, that makes this 16. Take care of my hydrogens, it makes that 18. So now if I count up my oxygens, I've got 16 times 2, which is 32, plus 18 gives me 50. So I know 50 divided by 2 is 25. Okay, same process. Start with my products. So I've got 16 times CO2, which just like before was negative 394, plus 18 times water as a liquid, negative 286. Subtract my reactants. I've got 2 times gasoline, which is negative 269, and then 25 oxygens, but oxygen is the element in its standard state, so 0. That first term is negative 11,452 kilojoules minus a negative 538 kilojoules. I need a parenthesis. There we go. If I add those together, I get negative 10,914 kilojoules. So, gasoline has a much larger heat of reaction than methanol, but methanol is used in race cars. So, you might be asking, well, why? Because gasoline has such a higher heat of reaction, but methanol burns a lot smoother, and so that is a bigger advantage than a higher heat of reaction. So it works out.